Hello everyone, it's Mr. Havenhill here, and we're here to complete the lesson on alternating series and absolute versus conditional convergence. And we're going to explore a topic that it's actually quite important. It sets a foundation for one of the most challenging parts of dealing with Taylor series and Maclaurin series and polynomials when we start studying the error involved in those approximations. Today's lesson is going to set a phenomenal foundation for the work that we're going to do a little bit later on. And so today's lesson is going to be focusing on error and remainder for alternating series. At times we might face an alternating series where we are simply unable to compute its sum. For whatever the reason, the tools aren't there, we lack the ability to compute it. What we do is we settle for the next best thing. We can ask ourselves, how close do you want me to get? How close do you want me to try to get to the actual value? And when dealing with such an approximation, we acknowledge that there's a slight difference between our estimate and the real value. And we're going to call this difference between the actual and our estimate, we're going to call that difference our error or remainder. And we would actually say if the actual sum of our series is S, and we're going to approximate it using some kind of partial sum, S sub n, and then what we're going to do is we're going to say that the difference between the actual and our estimate, we're going to go ahead and we're going to call that value, we're just going to treat it as a positive number, we're going to call that our remainder. And so what we can do is get that remainder as accurate as you would like it to be, and we're going to utilize a very special quality when it comes to alternating series. Now, let's go ahead and let's get ready to write some notes here. Here's something, here's a result, a theorem if you will, on how to find the remainder for an alternating series. Now, this is specific to alternating series. This does not apply to any other kind of series. If you have a convergent alternating series in which the terms are decreasing, then the absolute value of the remainder, R sub n, involved in approximating the sum by n partial sums, S sub n, it's going to be less than or equal to the first neglected term. That is, we claim that our estimate is going to be equal to the remainder. This is also known as the error. And because of the behavior of alternating series in which the terms are decreasing, what we have is that remainder is always going to be less than the term that you omit. And so we're going to also propose a special guideline for helping us to compute these errors and these or the remainder, if you will. In general, if we want to find, suppose somebody says we want you to determine 3 places of accuracy for an estimate, we can do that. If they wanted 5 places or 7 places, so on and so forth, we're going to follow the following guidelines. Suppose someone says we want k decimal places, and you're going to want to write this down too. K decimal places of accuracy if the absolute value of our error or our remainder is less than 0.5 times 10 to the negative k. So for instance, if we had 1 decimal place of accuracy, we would have 1 decimal place of accuracy if we had the following. The absolute value of E is less than 0.5 times 10 to the negative 1, which would be equal to 0.05. If we wanted 2 decimal places of accuracy, if the absolute value of our error is less than 0.5 times 10 to the negative 2, which is equal to 0.005. If we wanted 3 decimal places of accuracy, then we need the absolute value of our error to be less than 0.5 times 10 to the negative 3, which is equal to 0.0005. And this is the pattern that we would employ to try to find a specific level of accuracy. So, let's go ahead and let's try an example. Suppose we had this particular series. And what we want to do is approximate the sum of the series by its first 6 terms. Okay, so how would we do that? Well, when n is equal to 1, we would end up with negative 1 squared, which is 1, over 1 factorial. And then when n is equal to 2, that's going to be negative 1 over 2 factorial plus 1 over 3 factorial minus 1 over 4 factorial plus 1 over 5 factorial minus 1 over 6 factorial. And this is what the series looks like when it's expanded. And we know that this is this series is going to converge if we wanted to apply the alternating series test, and by the nth term, the limit is equal to 0, and then we have clearly that the terms are decreasing, and so we could say that the sum s sub 6 is going to be equal to, I believe this ends up being 91 over 144. As a decimal value, we would say that s sub 6 is approximately equal to 0.63194. Okay, so applying the theorem that we just developed to try to find the remainder or the amount of error that's involved in our approximation of this infinite series, the question is, how close are we to the actual value if we only used 6 terms? Well, we would say that the absolute value of s minus s sub 6 is going to have to be less than or equal to the very first omitted term. Well, since we did the first 6 terms, that means that our error would have to be less than or equal to the 7th term. Okay, so how do we find the 7th term? The 7th term is going to be 1 over 7 factorial, which is equal to 1 over 5,040. And as a decimal value, that's approximately equal to 0.0002. Okay, so here's where it gets kind of fun. In fact, this next part is going to feel a little bit like we're going back to our Algebra 1 days. What we're saying here, by the alternating series remainder, what we're going to say here is that the absolute value of our sum of the whole series minus s sub 6 is going to have to be less than or equal to 0.0002. Which means then, if I were to solve this absolute value problem, we literally have this, that negative 0.0002 is less than or equal to s minus s sub 6, which is less than or equal to 0.0002. And we could say then that s then, if we were to add s sub 6 to both sides here, and wait a second, what was s sub 6? What was our, there it is right there. So our s sub 6 was 0.63194. And we literally have that our sum, the sum of the infinite series, is going to be in between the following two numbers. When we take away 0.002 here, that's going to leave us with 0.63197, and our sum has to be in between 0.63197 and 0. And this time I'm going to add 0.2, 0.63197. Oops, I apologize. I made a little bit of a typo here. That should be 631. Sorry, I went one space over too far, guys. Sorry about that. 74 and 0.63214. So what did we accomplish just now? We want to approximate the sum with the first 6 terms, and our sum is going to be somewhere in between 0.63174 and 0.63214. As we increase the number of terms that we utilize in our estimate, then our partial sum is going to become even more and more accurate. Okay, so now what we're going to do is another example. Call this example dose. What we want to do is approximate this infinite series to 3 decimal places. Now, this is a different kind of question. We're actually trying to see how accurate we can get, and in this particular case, our standard of accuracy would be 3 decimal places. If we wanted 5 decimal places, we could do that. If we wanted 7 decimal places, we could do that. If we wanted 10 decimal places, we could do that. And so this approach is going to be a little bit different than what we just did. So what we're going to do is the following. We're going to first try to acknowledge that our series, if we ignore the alternating component of this, our series is simply going to be 1 over into the 4th. And we're going to let the entire sum of our infinite series be equal to that particular series. So we're going to say S is equal to, S is the sum of the whole thing. A sub n is 1 over n to the 4th. Okay, so using our remainder theorem, we've got this. You'll notice that I am not plugging in any specific numbers for n right now. I can't, because that's my unknown. My task is to approximate this series to 3 decimal places. And so I need to know how many values of n do I need for my partial sum. Is this going to be the 10th partial sum, the 12th, the 50th, the 1000th? I don't know yet. We'll have to try to determine this. What I do know is that the absolute value of the difference between the actual sum and my partial sum is always going to be less than or equal to my first term omitted. This ends up being 1 over n plus 1 to the 4th power. So here's what we need to do. This, I recommend that you guys write this down, including the verbiage that you'll see me writing down here, because I believe it will be helpful. We're going to need an n value such that 1 over n plus 1 to the 4th is going to be less than 0.5, and wait, what was our standard? 3 decimal places? So 0.5 times 10 to the negative 3. Okay? That's what we're going to try to do here. And if you wanted to, you could write that as 0.0005. Now, guess what we get to do? That's right, we're going to solve for n. Solve for n. By the way, for those of you that are kind of driven crazy by the fact that we're using scientific notation in a slightly unstandard manner, normally the digit here that we use is between 1 and 9. I'm only doing this so that the number of zeros that we employ here is the same number as my exponent up here. So if they wanted 3 decimal places of accuracy, I want to be able to just keep it simple as 3 zeros here. And so here we go. Let's solve for n. By doing so, we're going to have 1 over 0.0005 is now less than n plus 1 to the 4th. Well, this guy right here, that's just a fancy way of writing 2,000. So 2,000 needs to be less than n plus 1 to the 4th. Okay, from here it's not too bad. We would say that n plus 1 is greater than the 4th root of 2,000. And finally, we would say that n must be greater than the 4th root of 2,000 minus 1. Well, it just happens to be that this value right here is approximately 5.7. So our n value needs to be greater than 5.7. The smallest value that this occurs at, the smallest value of n where we can make this happen is when n is equal to 6. So we would say that our sum is approximately s to the 6, which if I went back up to my original series and utilized it, I would end up with 1 minus 1 over 2 to the 4th plus 1 over 3 to the 4th minus 1 over 4 to the 4th. Now that's 1, 2, 3, 4. I've got 2 more to go. Plus 1 over 5 to the 4th minus 1 over 6 to the 4th, which is equal to 0.946767874. And so what we have just done is we've said that this series, the 6th partial sum, that's going to get us our 3 decimal places of accuracy. So we know that this partial sum at least is accurate up to that point right there. Okay, we've got one more example that I'm going to share with you guys. And just to kind of prepare you ahead of time, the concepts are similar, but yet there's going to be enough of a difference that this is going to feel like a completely different kind of problem. And I just want to remind you that these kinds of problems they're very similar to the world of proofs several years ago when you had pre-calc honors. And it's been similar to a lot of the problem solving that we have done this year in BC so far. And that is essentially, it's nice when we can just imitate patterns over and over and over again, but really we don't get to see too many of those kinds of questions anymore. And so the questions are fairly unique, and this one is too. I'm going to ask you to determine the number of terms required to estimate the sum to 5 decimal places for this crazy series. You can go ahead and hit pause so you can jot that down, and then when you're ready, I'll talk you through the problem solving process. So go ahead and hit pause. All right, so we're looking at this thing and we ask ourselves, how on earth are we going to be able to do this? Okay, what we need to do is start off with the remainder theorem, the alternating series remainder theorem, which says that the absolute value of s minus our partial sum, the nth partial sum, needs to be less than a sub n plus 1, which in this particular case is going to be 1 over 2 times n plus 1 minus 1 factorial, and I believe that's 1 over 2n plus 1 factorial. So what we've got then, is the following. We need to somehow say that 1 over 2n plus 1 factorial needs to be less than 0.5 times 10 to the negative 5. Again, where are we pulling this from? That's the guideline that I shared with you a little bit ago. And so why negative 5? Because that was the number of decimal places that we were asked to estimate towards. Well, folks, we have a little bit of a problem here. Unlike the last example where we were able to solve for n, in our last example, we were able to come through and we can reverse engineer this, we can solve for n. We're unable to do that here. It's a little challenging to undo a factorial for a variable amount. So the only way we can try to solve this is the old-fashioned way. We're going to do some good old-fashioned plug and chug. Woohoo! So what we're going to do is we're literally going to simply try several values for n. Or, I'm sorry, n to try to determine a sub n plus 1. And what we're going to do is we're going to compare them to that standard right there. So let's see what happens. Let's let n equal 3. So that's going to give us a to the 3 plus 1, which is a to the 4. That is equal to 1 over 7 factorial. Okay, well, how does 7 factorial, how does that compare to 0.5 times 10 to the negative 5? So I believe that this is 0.000194, and we want to know how that compares to 0.000050. Well, that's definitely larger. So, okay, an n value of 3 is not sufficient. So let's see what happens when we let n equal 4. So that's going to give us a to the 4 plus 1. So that's a to the 5th, or sub 5. And that's going to be 1 over 9 factorial. All right, well, 1 over 9 factorial, if we plug that into our calculators, I believe is 0.23458. How does that compare to 0.000194? 0.005. Well, hey, that's smaller. So what we have then is the n value that we were looking for. We found the required n value such that our estimate was within 5 decimal places. So S sub 4 is equal to, okay, go back up to our original series, and 2n minus 1. Okay, so that's going to be 1 minus 1 over 3 factorial plus 1 over 5 factorial minus 1 over 7 factorial. We plug that into our calculators, and we're going to get approximately 8.4, sorry. I apologize. 0.84147. And there you go, folks.